Okay, now I'm recording. This is going to be a little bit cut off. Sorry. So you can't actually measure it inside of the rocket thing, because in the sensor you get there is going to get burnt instantly, right? It's going to get just incinerated. So what you can do is you can measure the external factors, right? You can measure external temperature of the outside of the rocket engine, and you can measure other things like how far did the rocket move, how much fuel does it use up, and you can use a Kalman filter to accurately estimate the inside temperature of the rocket engine. So how do we use that here in our orbit solving problem? We're trying to solve the orbit, right? So remember we had a whole bunch of radar pulses, right? So we can actually use all of these pulses and plug them into the data, or plug them into a Kalman filter to solve for velocity. And instead of using Lambert's equation to solve for velocity, it'll just eliminate the error by using all of this data. I wish I could explain that a little bit better, but I kind of don't understand Kalman filters super well myself. So that's basically what's happening here, right? So we have, I'm in the wrong one.
It seems like just law of averages.
Yeah, it's kind of an estimation algorithm. It's just an algorithm. So at the end of the day, it uses a lot of I guess I'll look at it right here. It uses a lot of these are NumPy arrays, and it uses like matrices and dot products. I tried to wrap my head around this, but it's really mathy. I mean, to be honest, you probably don't need to know any of this if you can just find a Kalman filter function or one like this, and you know how to implement it right way. That hopefully will be good enough. So what we do have to load here is this. We load this time scale, and this time scale actually comes from Skyfield. And what it does is it allows us to propagate these different positions through time. So we're going to be feeding each of the different time slices for the pulses into Skyfield, and we're going to use it to propagate all the different positions. So we're going to use this this inside function. So this all happens in this Kalman filter. Remember, it's removing the error in the velocity that we calculate. So if we calculate it, the way that we did last year in the competition with a straight line, obviously there's going to be a crap ton of error because that's obviously not one straight line. But if you have all these different ones, imagine a bunch of different straight lines that hop their way around these points. You're going to get kind of close to velocity, but you can cut out that error by using a Kalman filter. And that's kind of what we're doing here. So we have this giant loop going through all of the pulses. We're basically, this is all just feeding them into the Z array. So this one uses a different intermediate coordinate system. And this is the International Celestial Reference Frame. And this one is a little bit more to wrap your head around. But remember we talked about, so we have latitude and longitude, which everyone is hopefully familiar with, azimuth, elevation, range, which is not too bad, earth-centered, earth-fixed, earth-centered, inertial, also not too bad. And then we have this one. This is International Celestial Reference Frame. I have to remember that. So if you go to longitude, latitude, see all these lines here? Just imagine if you extend them out from the Earth. So take this circle of the equator and extend it outward, and these latitude and longitude lines, and extend them outward to project over the night sky. So if you're standing on the Earth's surface, you're looking up these lines. You're not standing at them. That's basically how this works, right? But instead of calling them latitude and longitude, you call it right ascension and declination. And the other big difference here that makes this kind of hard to wrap your head around, in this picture, it has the Earth as the center, but really what it uses at the center point is the very center of the solar system, which is the center of mass for the whole solar system. So you're kind of looking outward from the center of the solar system. So it's kind of hard to conceptualize, but it allows us to have the right, as so many things are moving in the solar system, it allows you to have a right frame of reference that is mostly unchanging, right? Because if we're using this frame of reference from Earth, Earth is rotating around the sun, the moon is rotating around the Earth, Saturn and Mars are moving all over the place, and it's really hard to have a consistent frame of reference, which is why this was created. So this is the intermediate form we're converting to here. And we have this. Yep.
Really quick. So can you go back to the image?
Yep. Oh yeah. Yes. Yep. 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 Thank you for that. One other thing I forgot to mention about this, so that your lines of declination, those are measured in degrees, but your vertical lines of right ascension, those are actually mentioned in hours, and that's because they use the sun, um, the sun as a kind of a reference point, and just the lines go around 1 hour, 2 hour, 3 hour, all the way to 24 hours. So that's just kind of how that's used. So we convert to this intermediate form, and we're going to chuck everything into this array. It says so it's three positions and then time at the end. Okay, and then we're going to go through the Kalman filter. I can't explain super well what this is and all this mathy stuff. Sorry. I tried to learn it. I'm still trying to learn it, so hopefully I can get better at it. But it's going to go through a big loop of all of the pulses, and it's going to run this thing to calculate the velocity for all of the pulses. The initial state it does not use. I guess is Kalman filtered. Is not Kalman filtered. So there's the initial state, and then all the rest of the states go through here. Yeah. So I can't really. I wish I could describe a little bit more what's happening here, but I just can't wrap my head around the math. But basically, we're going to go through that, and it's going to just magically return the orbit. And the orbit is going to be in Keplerian elements because of this. This is a pause time to Kepler. I can talk through this one because it's a little bit more, makes a little bit more sense. But this is where you're going to get the so A is going to be your semi-major axis. I forget what omega is. Actually, I kind of forget. I think this is anomaly, true anomaly. Oh, actually, no, we actually have them. I should say here. Oh, good. Yeah, so true anomaly is this little. I don't know the Greek alphabet. Sorry. So yeah, right angle of ascending node is omega. This one's perigee. This one's true anomaly. Inclination, eccentricity, semi-major axis, and that's kind of like an industry standard for using these kind of symbols for this kind of thing. So it's where'd I go here? So all of these are calculated in this, but there's going to be a lot of error. The Kalman filter is what's going to calculate it a bunch of times and remove that error. Is that pretty? Is that okay to conceptualize? Anyone have any more questions on that? And that's basically, I guess I'll run it here. This is radar without the 2. Oh, sorry, that's the old one. And there it is, it works, right? Gives us the flag. And just I'll put the 2 there to show you that the 2 different ones that ran and succeeded. Well, okay, well the numbers were there. I forgot I commented out that stuff. They both work. Those are 2 different solutions. Now all the write-ups I saw only used the Lambert's version. I guess because the Kalman's filter is kind of hard to wrap your head around. But the official answer had the Kalman filter. Now you have me curious. I'm just going to print out the elements here and just see how different they are. Yeah. Mm-hmm. Nah, this is a cybersecurity competition first. It's not a rocket science, rocket engineering thing. I mean, it kind of is, but that's secondary. Yeah, you can look at the differences here. So the first one used the Lambert's equation, and you can see the semi-major axis has, it's about 47. I think that's in kilometers off. There's about less than 1 degree, or I guess eccentricity is dimensionless, less than one whatever of eccentricity. Inclination's pretty close. Right angle ascending node is pretty close. That's pretty close. Anomaly is pretty close. It looks like the only one that's really different is the semi-major axis from the calculation, so it's not too far off. This date time one is I just printed the array, so it's truncated off of this one. But that's pretty much it. I could go through and talk about like what we were thinking with the library that we were creating. I already showed a little bit of it, but we have all these different disparate tools, right? We have tools, we have these Python libraries, and this is by far like definitely not comprehensive. There's a whole bunch more. And what are where'd it go here? Yeah, so this is our repo for our space calculator library we've been kind of making, and we've got our own branches here, so Nate's branch and my branch, and we're just trying to mostly find wrappers around these things, if anything, to keep them in the same like units of measurement, so that we're always using kilometers, always using meters, and make things so that they have like really simple like just dot notation for doing things. And I can kind of click on one thing for an idea I had that kind of stepped away from now. Yeah, so if you have these different classes. A satellite's a class. A satellite has an attitude. A satellite has these maneuvers, and then orbit is kind of like the base class because this is where you're going to see all the different semi-major axis, true anomaly, that kind of thing. And the idea is basically instantiate an orbit like satellite. To orbit equals and then a bunch of Keplerian elements, or you could do orbit equals and then have it instantiated from like state vectors or from azimuth, element addition, range, and you could just instantiate it anyway, like however you get it from the problem. And then you could do you can attach it to a satellite, right? And then if you wanted to get a new orbit, you could say, okay, this is the new orbit, and then you could have it automatically calculate like the maneuver or something before then. This is kind of something I a little bit like stepped away from now, just because it's a little bit much and there's too many different like obscure libraries and obscure like APIs that connect to weird coordinate systems. They're just really hard to get to play nice together. And so what I'm doing now, and everyone is welcome to do this, is, do I have it in this one? The test space calculator? Yeah, I'm solving problems, but I'm trying to solve them as unit tests. Okay, so this is not this problem, this is a different one. But basically, this was the I like to watch one that I saw like a week or two ago. And you're given a 2-line element. You parse the 2-line element, they give you a time, and then you load this time scale. And you do these calculations, right? You just instantiate a satellite, and then when you do your calculations, it's going to assert that your answer is in the right number, right? And you can actually check the repo there to see what number they're looking for and how they calculate it to make sure it's done. And hypothetically, if we were to go through and solve all of these, all of the problems from Hackasat 2020 and 2021, and we'd have like little kind of unit tests for each one, we could kind of experiment and see if we have our own library, see, okay, this works for all of the libraries, this one doesn't work in Mr. Radar, this one doesn't work in this program, our problem. And it'll be kind of easier to develop from that point. And if we get nothing out of that, at least we've gone through all the problems, right? So that was kind of my thinking with that. We have a channel here for that, space calculator development, and everyone's welcome to do that too. Yep. Yep. Yeah, absolutely. Hmm. Yep. Yeah. Yep, and if you go to the general channel in this Discord, I have pinned the location of all the different challenges from all the Hackasats and different write-ups for them. So you can, let's see if I can pull one up here. Go to Hackasat, and it's the, I forget how to say his name, Kromulinsk, something like that. It's his, yeah, I got it up. And you can see all the problems here, and this is where they hosted them. And you can just launch them, solve them on your own. They serve them in Docker containers, which is what I have done here. So if I go like Mr. Radar, just tells you how to run it with, it tells you how to build the container with Docker. It's a little bit more involved to run it. Yeah, it gives you the problem, and you can actually look through. So they have the challenge, and this is how the challenge is written. Okay, so you can see that they spit out all of the information here, all the the prompts, and you can see what they're looking for specifically for the answer. Yep, see there it is. They're comparing the answers, so it has to be, within these thresholds of error. And you can see kind of how they're calculating their thing here, but they also provide a solver, right? Which tells you how they solve it. And this will hopefully look familiar, not this one. They have a whole bunch of, they actually went really in the weeds for the solver here. A lot of the stuff you didn't need, but I think this Kepler, maybe it's not this one. Yeah, PVT2 Kepler. That was one of the ones I used. I just kind of renamed some stuff to make it more sense. That was one of the ones I used in Mr. Radar. And yeah, radar.py, that was it. And this is where the Kalman filter is. Yeah, the estimate orbit. It's Kalman filter. I literally copy and pasted this and just renamed some things to try and make sense of it and kind of went through it. So this is how they tell you both how they set up the challenge and how you solve it. So you can kind of work through it this way, and then you can also look through all the different teams and see how they, the different GitHubs, so the different teams write-ups to see how they solved it during the competition when they didn't have the answers on hand. And I recommend reading as many write-ups as you can because it really gives you a different idea for how other teams think and different ways to solve problems. That's pretty much all I have. So unless anyone has questions, I'm happy to talk more or look through things. I really think we have like a solid chance of like at least making the top 8 this year. Like if you go back to the scoreboard, like there are a couple of names, like big names here, PPP, Solar Wine, pulling Ken into space, but there's some others here that I think we can definitely beat out. So I think we actually have a really solid chance of making it. Yeah. Mars or bust. Yeah. Yeah. I think we're already. Yep, and we're already ahead in preparation. Like we've already had 2 little meetings with and gone over stuff. So that's more than we did. More than I did last year. So. And if you look at like how we do the competitions, you can look in the Discord on the left here. We have these competition rooms, and we'll generally just rename those to like a challenge name, and you can just hop in, and hop out at will, wherever everybody will be working on a challenge. So it's really, really flexible how we do it. Just right here from this Discord. Yeah, I looked at registration stuff. I didn't see anything yet. So yeah. Hmm. Yeah, I kind of assumed like so the last year and I think the year before that they kind of had like unlimited number of like team members and stuff. You just um, you just basically register yourself to a team on the page, and you can have any number of joins. So I assume that's how it is again this year. So hopefully, we can have as many people as we can in here, and the more the merrier. Thank you. Hope you guys enjoyed it. I'll see you next time.